The lean and fast C++ program for training dense deep learning structures is now significantly faster because training runs now parallel. This means that training speed is now 2 to 6 times faster, depending on the problem and based on conservative estimates. The CPU is utilized as much as possible, and denseNN still does not require a GPU. The parallelized version denseNN 1.30 is available for download for Windows as an MSE file and for compilation on Linux system via the GitHub repository Suprenum denseNN. This video is not really necessary because the training workflow has not changed and the parallelization of the training process is carried out in the background without requiring any additional input from the user. The video training dense networks with the C++ EigenNet project is still relevant, and you can watch this video as motivation to use denseNN. So welcome to the video Parallel Dense Network Training with denseNN. As mentioned in the introduction, the video training dense networks with the C++ EigenNet project is still relevant. And I'm again using the R script dense example to demonstrate parallel deep learning training. However, I'm taking a few shortcuts here and going straight to the training section after setting the working directory. I set the trainings parameter as shown here and start the training. In addition to the well-known information output, details on process utilization are also provided. Compared to the training with the MNIST dataset in the video mentioned above, parallel training per epoch has become around 4.5 times faster. The speed increase factor naturally depends on many factors such as the hardware used, the training parameters and of course the dataset. Of course, the new parallel denseNN version 1.13 can also be used under Linux. How to install denseNN under Linux is described in the video Deep Learning Structures with denseNN on Raspberry Pi 5. This is just one example, of course, because I don't have any other Linux systems available at the moment. The CMake list file has been adapted accordingly and is available alongside the C++ files on the GitHub repository. I start training for the MNIST dataset on the Pi 5. Here too I can see the number of threads being used. However, the training time per epoch has increased significantly. It seems that here is a parallelization overhead. This needs to be checked now, so I abort the training on the Pi. By setting export OMP num threads to 1, I disable parallelization on the trial basis. And after a short time, I get the training time of around 10 seconds per epoch. That is familiar from the video mentioned above. This is a clear sign that the management of the parallel process is not optimal for the ARM processor. I will try to optimize that. I set the number of threads to 2, restart the training, and check the process load with the task manager. The expected is around 15%. Unfortunately, the training time per epoch has roughly doubled again. If I increase the number of threads to 3, the training time also getting worse, which is also in line with my expectations. Well, due to its architecture, the Raspberry Pi 5 is certainly suitable for small deep learning training tasks, but definitely not for serious projects. And that brings me to the end of the video. I hope I have been able to show that denseNN is a real alternative to the big environment such as TensorFlow and PyTorch for dense type deep learning structures. Despite the parallelization of training that is now available, denseNN is still very lean and, as shown, very efficient. I would be delighted if you try out dense and give me your feedback. See you next time.